Um, as you just saw, we will be recording this webinar today, so please bear that in mind. But thank you very much for joining today's webinar with the Center for Analytics, in particular featuring one of our analytics initiatives through Ophthalmo Corp. We're developing a multimodal foundation model for optic neuropathy. So we're very excited to have this webinar today. I'm Francis Jeanson. I'm the head of the Center for Analytics at the Ontario Brain Institute. The webinar, we'll start with a bit of background on the Ontario Brain Institute and the Center for Analytics, followed by a presentation by Ophthalmo. And we have Dr. Ehsan Amjadian and Dennis Athkin joining us today to present on their work through the Center for Analytics. Before we begin, I'd like to acknowledge the land, its nature, and its people. In particular, the Anishinaabe, the Mississaugas of the Credit, the Wendat, the Haudenosaunee, and every other nations, recorded or unrecorded, who have taken care of this land long before us. Land which we must continue to take care of together. So as I mentioned, I'll give a bit of background on OBI and the Center for Analytics for those of you who aren't really familiar. So let me start with a few slides to help guide this background. So as you may or may not know, OBI is a non-for-profit institute that really aims at accelerating research and discovery in the neurosciences. So we're really focused on supporting research excellence through collaborative efforts that are very multi-institutional and multimodal in nature. So we support research that are really spanning various types of brain disorders, from neurodevelopmental to mental health, all the way to neurodegenerative types of disorders. So we have a big focus around this collaborative research approach. We have also a big emphasis on commercial innovation. We really aim to enable early stage companies, startups, as well as medium stage and later stage companies to work closely with the research ecosystem so we can really catalyze this innovation for brain health. Ultimately, our goal is to have an impact on patient health and really enable this ability to translate these discoveries that are happening at the research level with commercial partners to the bedside, so we can have an impact and improve the lives of people with brain disorders, whether it's in the clinic or within the communities. At OBI, we've established major research programs that we call integrated discovery programs. And on the slide, you sort of see them as these big circles near the center. So we have CanBind, for example, that's focused on major depressive disorders. The PON network focused on neurodevelopmental disorders. The CPNet network focused on cerebral palsy. The COM network focused on multiple mental health disorders in children and youth. And finally, the Transcendent network focused on concussions in children, adolescents, and adults. Very important here is these networks really connect a large number of institutions across Ontario, Canada, and even beyond, as you can see through the number of hospitals and universities in this network. What we've done is really established a standardized approach for collecting the data that are being collected through these major programs, because ultimately these data help with the discoveries that need to be made. These data are centralized on our platform called BrainCode, which you see here in the middle of the diagram. So we have over 40 institutions connected through our networks, thousands of users on BrainCode. We enable data standardization, data federation, also data linking, and data analysis through BrainCode. This creates a real neuroscience data discovery opportunity. As I mentioned earlier, these programs really collect data across a number of modalities: clinical data, neuroimaging data, genomics, molecular data, and more recently, a lot of growth in the collection of wearables and sensor-based data. And this spans across these brain disorder areas that I mentioned before. So really creating a rich and deep set of data that can help with these generating new discoveries, better understand brain disorders in terms of maybe diagnostics, detection, prediction, and even potential treatments. So the BrainCode platform is really designed to be a multimodal data collection platform. It also enables data sharing. So we enable that collaboration within these programs that are multi-institutional, but also across with other collaborators that may be outside of the programs. We collect common data elements, which helps ensure that we can compare apples to apples between data sets. And ultimately, we enable data linking using privacy-preserving technologies so that we can even expand the value of these data sets. So we have a number of data that have been collected so far, and this is a quick snapshot of the types of modalities that have been collected across these programs. So we see here POND with clinical and imaging, CPNet, clinical imaging molecular, EPLink, Cambine, Connect, and Andri, all having multimodal data collected across the board. And you can access more information about these data sets and potentially submit a request for access to these data on the BrainCode website, which is listed down here below, braincode.ca. However, over the years, we noticed that there have been challenges with maximizing the value of these data. We need more skills in this space. We also need to accelerate the development of tools so that we can support better discoveries and even deployment of tools that can have impact on patient health. We also need to help labs and startups better translate these technologies to the bedside. And so this is where we had the vision a few years ago to launch the Center for Analytics. And this is really what we're focused on: building skills in neuroanalytics, helping accelerate labs and startups with access to high quality data, leveraging computing, and also sharing and building a tool ecosystem. And finally, helping with that translation of these tools and these methods so that we can translate them and have impact on patient health. And that involves navigating the regulatory pathways, ensuring that we have a platform that can provide high levels of privacy and security for the tools being deployed, and ultimately help even productize these applications so that the startups can have a platform that enables them to serve their tools to clinicians or to patients. So our webinar series is really aimed at highlighting some of these great innovations that we're supporting through the Center for Analytics. And you see here a bit of a historical list of webinars we've had so far this year. And today we'll be showcasing work by Ophthalmo Corp, who are focused on developing multimodal foundation models for optic neuropathy. And you'll see we'll have a few more webinars scheduled for this year, with another one coming up in December with Dr. Uher's lab at Dalhousie University. We also have, we will be announcing shortly the next cohort of analytics initiatives through the Center for Analytics, so stay tuned for that. These will be announced in the new year. We have a number of resources that we make available online, including the methods tutorials that essentially serve as sort of guidance and tutorials on how to use these technologies that we make available on our GitHub page. And you can scan the QR code here to access those resources. We also have these webinars that are being recorded that are uploaded to our YouTube channel, which you can access through this other QR code here on the right. So we hope this will be a helpful resource as we build the number of tools and methods tutorials as well as the webinars. So thank you for this time to provide you with a bit of background on the OBI and the Center for Analytics. I'll now be passing it over to Ophthalmo, and I wanted to introduce our guest today with Dr. Ehsan Amjadian, who is a well-known leader in AI. So I'll stop sharing. He's Associate Professor of Computer Science at the University of Waterloo and the CEO of Ophthalmo Corp. We also have Dr. Dennis Askin, who's a former IBM AI engineer, a postdoctoral fellow in generative AI, and he's the Chief AI Officer at Ophthalmo Corp. So thank you, Ehsan. Thank you, Dennis, for joining us today, and we'll hand it off to you.
Thank you very much. Dennis, if you can kindly go ahead and start sharing the screen. I'd like to start really by thanking the team at OBI, Francis and everybody else for the opportunity. We have utilized much of the resources that has been provided to us, including the compute infrastructure that is pivotal and critical for both training, fine-tuning, and testing larger models, including foundation models. Let me start with the brief intro, and maybe Dennis, yes, you can. There you go. Thank you so much. So maybe start by telling you who Ophthalmo is, and then after that we move more towards the experiments and where we are in our journey. So we can go to the previous one. I'll announce when I want to go to the next one. I appreciate it. For this presentation, we call it the path to a world where everyone sees, and that's kind of our motto. We want to have a world where blindness is not an issue. So that's ultimately, in one phrase, our mission, our ultimate goal. We can move to the next slide. Thank you. Okay, so yeah, a few points as to why we came together and why we exist. So eyesight is often cited as a most important sensory mechanism that humans utilize and use and have been bestowed upon. We are a STEM-based AI company that envision a world where everyone sees. So that's where we want to go, as mentioned earlier, and to do so with the clearest vision. In Canada here, we are very fortunate to benefit from accessible healthcare to all Canadians. It does come, with a cost, and the healthcare system now more than ever, can benefit from smarter healthcare that lifts the burden off our medical professionals, especially doctors, without incurring an insurmountable cost to the public. And we found it to be the right time to contribute to this important cause. And that's really why we exist. And hopefully all of that can lead to the quality of care that is a right here in Canada, and everyone will benefit from for the years to come. As a society, we've decided we do not want to compromise on our health. So let's move to the next slide. So let's take a look at the challenge. When doctors make decisions, they use a multitude of modalities and data points. Imagine a patient walking in. The doctors usually have already studied their background, their medical background. Again, across all modalities. There could be images, there could be text. They visually inspect the patient's physical aspects. Are they feeling well, so on and so forth. Are there signs of headaches or discomfort, so on and so forth. Are they discolored, or they also hear out their chief complaints. Why is it the fact that they're referring to me? They look at their systemic health, their entire body health, even specialists, and they carry out various examinations, including for optometrists and ophthalmologists, looking into the eye via various imaging techniques, including fundus images, as well as OCT. The latter, the former you see at top right, the latter you see bottom left. And so you take all of that information as a doctor, and there will have to be some time that you spend with the patient, right? So that is timely, that is costly. We really hope to reduce that burden as much as possible in a trustworthy, secure, and private manner that will assist doctors where it matters, so that they can spend their time most efficiently, hopefully more and more time with patients and across their critical care that they provide to the patients. So So let's take a quick look at the specific, image at bottom left. This is an example of glaucoma OCT image. The bottom image is a patient with glaucoma. The one on the top is a patient that's healthy. And you can see the nerve damages right at the macula, at the center of the eye, right? So why that matters, it's usually very important to be able to see this in layers, as opposed to the fundus image, that's a flat image, right? So it's very clear. And I think in addition to in addition to conditions such as glaucoma, whatever condition the patient may be facing can be indicative of other, perhaps even more serious systemic disorders. So, for instance, we know that optic neuropathy and neuritis specifically is associated with MS, which is a serious systemic disease, and we need to act fast. So this acting fast, although we're focused currently, on really the eye and eye health, and that's our mission, but it can really, save, lives. So let's move to the next slide. And we can skip that one. I think Francis Conley has introduced us. So about our mission, short term, would like to take that burden off the doctors as much as possible. Midterm, we want the AI to be, not only assistive, but proactive in assisting. So predicting what's needed and helping the doctors in the most intelligent and context-aware manner. And long term, we really hope for blindness not to exist. Not existing one way, it could be by catching things early on. Unfortunately, still patients with glaucoma go unnoticed, despite the professional eye care that's provided in a leading country in healthcare, including Canada. We still see that either patients do not go for whatever reason. We still have, and this is only one of the blinded diseases. So really hope to go to the world where this doesn't exist, either because it's prevented or because it's treated. And right now, when the nerve system gets damaged, there is no immediate way or approved way to recover that nerve. So let's move to the next slide. So I think here is where I pass it over to you, Dennis.
Absolutely. Thank you very much, Ehsan. Hello, everybody. I would like to present as the AI officer here, just kind of the preliminary work that we've done thus far that will be indicative of what we want to continue to do in the future. So we start our mission by developing AI for eye disease detection, which is very much a new field. And there are a lot of things to be discovered along the way, and we certainly are ambitious to be the trailblazers in the field. Now, due to the resources available, a reasonable place to start for us was glaucoma detection by computer vision. So computer vision is a big field in which we use AI models to take images and then classify them under a certain category. And we can actually train these AI models to basically come up with arbitrarily many different classes that we want, and for them to classify them according to the classes that we want. Here, what we wanted to do was to have our AI take in an image of an eye and classify it under a normal or an eye with glaucoma. So it's a glaucoma detection vision model. So let's go to the next slide. What we worked on we started with fundus images, which is a really good place to start because they are in the literature in glaucoma detection via imagery. Fundus images are the most common way of trying to come up with this classification. Now, first and foremost, for those of us who are not familiar, let's talk a little bit about what a fundus is. The fundus is the interior surface of the eye, specifically the back portion that can be viewed through the pupil. And we have these really valuable data sets out there of fundus photographs. And these data sets kind of mix photographs of fundus that display glaucoma and normal funduses, which we can utilize in order to train our classifier. A fundus photograph or fundoscopy image is a specialized medical image that captures certain portions of the eye that are essential in categorizing an eye image under one with glaucoma or normal. One is retina, the other is optic disc, where the optic nerve enters the eye, macula, central area responsible for sharp, detailed vision, the blood vessels, and the fovea. So how fundus images are captured, I would like to briefly talk about this just so that we have a more clear understanding of the kind of imagery that we utilize in order to detect glaucoma. A fundus camera is a specialized low-power microscope with an attached camera. It shines light through the pupil and photographs the reflected light from the back of the eye. And the resulting image shows areas of the eye that are important for us to see if there is an early onset, let's say, of glaucoma, later stage. And what it shows is a circular field of view, reddish-orange background. We'll see an image very soon that displays all of these. A bright optic disc, dark macula, and red blood vessel networks branching across the retina. So all of the things that we would like to see in order to decide if an eye has glaucoma or not. Now, you can see the imagery here. The fundus data sets have images that look exactly like this. And these are the images that, these are the data sets. These are the types of images that the data sets that we use contain to train and test our classifier on. We ran tests on three what we call benchmark data sets. These are data sets that are commonly and constantly referred to in the literature because they have been curated specifically for the task of building a classifier, a glaucoma detection classifier. They contain normal eye images as well as glaucoma images, and some of them are unbalanced in terms of the representation of the classes. There might be more normal eye images than eye images with glaucoma, for example. This is done on purpose. This is done in order to make the task more complicated and difficult for the classifier, because the more images of a certain class we have, the better the engine is at classifying with respect to that specific class. And we want to challenge the classifier because ideally what we want to build is a state-of-the-art classifier that does really, really, really good in glaucoma detection, despite the fact that it was fed more normal eye images. So these fundus data sets that we used, again, these are constant in the literature, are Auriga G1020 IPAX version 2. Auriga dataset is a specialized glaucoma dataset with optic disc annotations and a cup-to-disc ratio measurements for clinical diagnosis. G1020 contains large-scale multi-ethnic fundus image datasets from various populations. Again, we also want our data sets that we train our classifier on to be as diverse as possible so that we can use them to generalize. We can use the classifier to be able to accept data from multi-ethnic funduses as well as different stages of glaucoma, so that our classifier can classify with respect to a diverse set of images. And the IPAX version 2 dataset specifically focuses on diabetic retinopathy screening dataset and it's repurposed for glaucoma detection. We specifically use this dataset because it's actually a second version of a previously used dataset, but it's more improved. And we want to obviously create a classifier that focuses on the latest datasets out there. Here are some details about the size.
Is it okay, Dennis, if I interrupt for 1 second regarding IPAX? So IPAX has been created in the past before. However, during the past work, we've accumulated these images and highly standardized them. So it was not originally created for the computer science audience. It was created for a medical audience where you can go through the data and you can examine the data and perhaps train the new doctors. And we noticed that if that's going to be used for AI application, it needs quite a bit of pre-processing. So what we've done, and I think this can be contributed back to OBI's platform, pre-processed all this data so that they're immediately available and immediately useful for machine learning experiments. And that's it's IPAX Lite V2 version. Over to you, Dennis.
Thank you. So yeah, our data sets were quite big, some of them being in the thousands, G1020 and IPAX, and Orga being in the hundreds. They all contained a training and test sets, and they were, again, unbalanced in terms of the number of instances of normal eye images versus glaucoma eye images. Again, this is done on purpose, because we want our classifier to excel in glaucoma detection despite the fact that it has been trained on more instances of normal eye images as opposed to glaucoma images. So we tested a bunch of classifiers. Here on the left-hand side, what you can see are a list, the bullet points for each data set are basically names of different classifiers that we have tested our data sets on. And we locked the results. These are the percentages that you see here are measures of accuracy, which is just basically how many of the test set images were correctly classified as normal eye images or glaucoma. And we've realized that a particular model that we used, the one that is highlighted here, bolded, that was actually fine-tuned on glaucoma images, gave us the best results. For Orga test set, our result was 95% accuracy, which is very high. For G1020 dataset, it was 93%. Now for IPAX, it was 84 at first, but we will see now in the next slides that we've actually been able to, using a process called fine-tuning. In other words, doing our own training, we were able to raise its accuracy to 90% as well. So here, the reason why we like to share kind of the results that we have is to show that we're able to use data sets for glaucoma detection that are benchmark data sets that are used in the literature constantly, and we're already able to get results that are quite satisfactory. I'm not, because of the time constraint, I'm not going to go much into the details of the type of classifier we use, but in the question section, please do ask me any questions that you might have. But the specific classifier we used, which has the structure, the architecture that we see kind of a diagram of in the right, was based on a model called a ResNet 50. And what that is it's basically what we call a vision transformer model. These models, roughly, what they do is to take images, and then they apply different filters on the image as the image progresses through its different layers, subsequent layers. And by placing these, by adding these different filters on top of them, different representations of the same image are made possible, and the engine learns to have multiple different representations of the same image, which then makes it understand all the different, how all the different pixels in the image actually correspond to what, let's say, for example, normalcy or glaucoma. That would be a general explanation. If you would like me to go into the technical details in the question section, I'd be more than happy to. But basically, the model that we used was a vision transformer model. We did some pre-processing too. This is actually our contribution as well, because one doesn't necessarily have to do image pre-processing, namely modifying the image that we send to the model prior to actually sending it to it. But we've seen that this actually doing this increased performance significantly. We resized images to a specific model size. This allowed the classifier to focus on only regions of the image that are very pertinent to glaucoma detection. And we also did some rotation of the image as well as adding color jitters. Now, why would we want to do that? This actually helps the model's ability to learn different representations of the images, which allows it to have a better understanding of how to look for instances of glaucoma in diverse set of or diverse format of images, which increases its performance and classification. So as mentioned, we gave the results already. We have some more for those who are data science oriented. We obviously logged not only results of accuracy, but other results that are standard in the literature, such as precision, F1, and recall. These measures refer to our classifier's ability to classify the correct images as correctly. Or in other words, if it was to classify a normal eye image under glaucoma, we would see a much lower performance in some of these measures. But as we can see, all of the percentages here are all within the 90 percentile. For the Origa result, the accuracy was 95%. Again, it was very high. And again, all the other measures like recall, F1, and precision are also high. Now, the IPAX data set, if you recall the first reported, let me actually go back so that we can take a look at it. Our first reported result was a baseline accuracy of 77%, which was quite low. But then what we did was to apply what we call fine-tuning in the literature. And what that means is to train the classifier that we use on the train set of the IPAX by using different training methodologies in order to then test the data set again on the same classifier that we have trained, to see if we can see an increase in the test performance. And the idea is, because we have now trained it on the same data set, or the train set of the same data set, when we test it on the test portion, we should, because the classifier is now a little bit more understanding of the kind of imagery that is in the data set, the performance should be increased. Now, when we use just regular fine-tuning methodology, the increase that we saw was about just 7%. So we went from 77% accuracy on this data set with our classifier to 84. However, when we developed our own fine-tuning methodology that uses a much more complicated recipe, which the details of which I'm also happy to go into, we were able to actually take the accuracy from 77% to 90%. And this was a work in progress. This was quite a bit of work for us. And this is our contribution. We believe that this particular training methodology that we used for this particular classifier and data set is most likely going to be generalizable across different, on the same classifier with different data sets, which initially might not give us good results with our first testing. But now, having learned a methodology and recipe of fine-tuning, we plan to use this recipe or variants of it for different instances, for different data sets running on the same classifier as well. And it doesn't have to be necessarily the exact same classifier that we used, because most of the classifiers that give good results in this particular task have a similar architecture. So it is our conviction, based on experience, that the particular training methodology that we utilized here, that gave us quite a boost in the accuracy, will actually be generalizable in our future tests for glaucoma detection, or perhaps other eye disease detection tasks. So what is next for us in terms of the tests that we're going to run and our use of AI? Well, obviously, we would like to test on more data sets with also glaucoma data sets, but also data sets with different eye conditions. There are quite a bit of data sets out there that have more than two classes, not just normal and glaucoma, but data sets for classification with respect to multitude of eye conditions. So we would like to definitely continue our process of using our classifier and fine-tuning our classifier with respect to different data sets, eye imagery data sets. Continue testing our fine-tuning, namely learning methods. We have seen a promising increase in accuracy with respect to the IPAX dataset with the fine-tuning methodology that we have developed. We would like to actually take that. We would like to see A, if that generalizes across other data sets as well, and B, if not, what are the tweaks that we need to make that give us optimal results when it comes to eye disease detection. Lastly, we want to test on generative models to compare performance. So the models that we've used were non-generative models. So they're not like GPT, say. The transformers that we use or the classifiers that we use do not give answers. You cannot interact with them. They only give you a class. We feed an image and we get a class as normal or glaucoma. However, one can use models like GPT, generative models, chatbot models, to give examples of images, normal and let's say glaucoma in this instance images, and then say, okay, based on what I have given you, is the next image that I'm going to give you, does it contain glaucoma or is it a normal eye image? So in the literature, we use this, we call this a few-shot prompting. And we can use generative models to actually predict classes as well. So that's one of the next steps that we want to take as well.
So if I may, very briefly, we needed to start with encoder-based models. And as we move on, we have a really solid now baseline to see if decoding-based models will have any additional contribution regarding the performance of the detection of blinding diseases such as glaucoma in our experiments. So that's why that order exists. Obviously, encoder-based models are more efficient. Decoding is, if you add decoding and encoding, it would be much more costly. So that's the main reason for this order. Yeah. Dennis, are we concluded? I think so.
Yes, one last point I can add is another thing we have been actually entertaining doing is using ensemble models. So having a voting mechanism, if you will, we can, instead of using one encoder model, one classifier, we can run in parallel, say, 4 classifiers, all of which individually give good performances. And let's say for the glaucoma test, feed the same image to all 4, have them classify the image as normal or glaucoma. And if 3 of them agree that it's normal, then we vote and we select that as the answer. If 3 of them say, no, it's actually glaucoma, and one of them says it doesn't, we classify it as glaucoma. So voting mechanism with ensemble models is another thing that we're entertaining.
Over to you, Francis. Thank you. Thanks, Dennis.
Thank you.
Thank you, Ehsan. Thank you, Dennis. Yeah, great presentation. Really exciting work. I have a few questions, but I'll maybe see first if there's anybody on the audience that would have a question. If you do have a question in the audience, feel free to post it in the chat box or raise your hand and unmute. We feel free to ask any questions. So I'll just wait a second to see if there's anybody.
There is one question that was sent directly to me. I need a bit more clarification. So I read LGSF net published last week in the Ophthalmologist compares to ResNet as well as all using the same same open fundus data images. Other comments. So I think they're asking if some recent study that has been published uses the same data set. So the data set that Dennis has kindly walked through are some of the most well-known ones that are publicly available. There are data, obviously proprietary data that are used in industry, and we do have access to. So we want to expand the experiments in the later phases. But as to that particular study, if you send me, a link to this study, I'd be happy to take a look and give you my comments.
That's great. Thanks, Ehsan. I don't see any questions at this point, so I'll just ask my own. I have a question related to, so Dennis, you described sort of the training of the model on these different data sets. Is it this, so there's model and model. There's the model before it's trained, as you know, it's usually randomized, weights, et cetera, with just the architecture, but then you actually train it on the data. You mentioned those 3 data sets. Do you train the model once on one data set and then use that trained model to then train it on the next data set and then essentially incrementally improve the model by seeing more data, or did you retrain the model every time on each data set?
So that's a really, really, really good question. So we only actually trained once for the IPAX data set. So that was the only time we fine-tuned, right? The model that we used the encoder model, it was already fine-tuned on the glaucoma data sets. So going back to your question, we trained only once ourselves, fine-tuned only once. So we used it we basically fine-tuned on the IPACs and tested on the IPACs. In order to increase the performance. All the other data set performances came from the already fine-tuned vision encoder that we used. So basically, we didn't go through the process of merging all the data sets, training, and then testing on every one of them, or going through the process of fine-tuning for each either. We only fine-tuned for the IPEX dataset and tested on the IPEX datasets. So we didn't, after fine-tuning on the IPEX dataset, we didn't use that fine-tuned model to test on the other datasets.
Right. Do you think that could potentially help him with the accuracy of the model, or is that unnecessary?
I believe that it would. So actually, what I do believe is that in our next step, the most reasonable thing to do is going to be curating a whole large train set by merging the train sets of other kind of benchmark data sets out there, and fine-tuning the large language model that we already have here on that, and then see what kind of performance we get across the board for all different data sets, not just one. One thing we need to be cautious of is catastrophic forgetting. Because when we merge all the train sets together, we're going to get quite a sizable train set. And we do not want the data that this particular vision encoder has been fine-tuned on to be forgotten as a result of the new data that we feed it. So that is going to be one of the things to keep in mind, but there are ways around that too, obviously. But yes, so that will be the next step for us, to curate our train set by merging the train set of different benchmark data sets and actually feeding that to fine-tune, as opposed to fine-tuning on only the train set of one benchmark data set.
Right. Sorry, quick addition. The reason there was so much focus on IPACs was that our mission at first was to replicate a lot of these, the existing methods that are out there, and see if we can actually verify their results. For the results that were already above 90% F-score, we satisfied as that, and IPACs didn't. So we spent a bit of time there. From this point on, obviously, it really matters for this performance to increase, but also to look at other different methods as described earlier.
That's great. Yeah, thank you. I don't see any other questions so far, so maybe I do have another one.
Yes, please.
You had mentioned first you mentioned the use of some of these these models are LLM based, so there's a language component too that they've been trained on, as far as I know. Is there the ability then to kind of query the model with natural language, or is that like a future phase?
That's a great question. So we would only be able to do that with generative models. The models that we're currently using, being encoders, they're vision encoders, so they only accept imagery. They basically transform, they work on pixels. However, once we start testing with the generative models, absolutely. So they accept both text as well as images, and we can, in fact, that's precisely how we have the decoder, the generative model, output only a class token as opposed to a whole answer, such as glaucoma or normal. So we need to actually use prompt engineering to do that. So yes, it's a multimodal thing, but we need to use a generative model in order to give it instructions through text.
Great.
And sorry, something again I'll add to what Dennis mentioned is these models are not small by any means. So, one of our models is 300 million parameters. But obviously, if you have multimodal generative models, really the size would increase. But the target was at first to see what, as mentioned earlier, what the encoders can do on their own to establish that baseline. A lot of the even highly recent literature, very recent literature, focuses on the encoder-based models, just because maybe they're faster to run with the resources as hospitals or kind of medical industry uses, as opposed to the big tech.
Right.
They're faster, and also they're easier. One can fine-tune them in a much easier way. Obviously, there's a huge difference between 300 million versus 7 billion, 12 billion, 250 billion. And that's why usually instead of fine-tuning the generative models, we use few-shot prompting, giving examples to it. However, in some preliminary tests that we ran, we realized that it's not really easy for the generative models to learn a great deal from giving it even hundreds of examples of, say, glaucoma versus normal eye imagery. And I think the reasoning behind that is that these decoder models have been trained on trillions of data. As a result, it's very difficult without changing weights to try to have them learn a great deal from, say, couple hundred images that we feed it. It's not nearly as easy a task for it to learn from, to actually generalize what it learned from few shot examples to future images. Whereas because the encoder models are smaller, we can change the weights and fine tune them. And that actually informs them much better about that particular task. In other words, given that they are far more laser focused, or they're designed to do one thing and one thing alone for our tasks with the encoders that are fine-tuned for, let's say, eye disease detection. They have a much higher likelihood of giving us better results with classification, as opposed to a generative model, which is trained on the task of giving an answer about anything.
Mm-hmm.
Right?
Yeah, that's really good. So as a result, do you think like deploying something like this in the clinic would mean it'd be like sort of I mean, you talked about ensemble models, but in a particular context, do you think it would be like a multimodal approach, but with different models doing different things to ultimately support clinical, the clinical sort of decision making or clinical work essentially that's happening in the clinic? Do you sort of see that versus having just one big model that does it all?
I think so. Some distributed, let's say, for example, using the encoders for the classification based on the images that were classified under glaucoma by the encoder, feed those images to a generative model to write a report, let's say.
Mm-hmm.
So, some form of
Yeah.
pipeline that involves different models.
Right.
It seems to me. What do you think, Ehsan?
Oh, that's exactly it. You got 100%. Yeah.
Fantastic. That's great. Well, thank you very much. We're reaching the end of the hour. I don't think we had any other questions from the audience. I don't see hands up or comments. So I think we will close up at this point, but I want to thank again Ehsan and Dennis from Ophthalmo for joining us today and presenting on your very exciting work. This is I think a phenomenal area to be able to have an impact on. It's a clear gap, I think, in the health space to support eye care. So we're really excited to see a progress with Ophthalmo. I will share. So if you don't mind stopping sharing, I will share my screen again.
Absolutely.
For who are just sorry, I'm looking for just to provide access to the links to our webinar. So including this webinar will be posted on our webinars link here on the right. So I want to share that resource again. And make sure to follow up on our methods tutorials that will also be coming out from all the analytics activities that we have currently going through the Center for Analytics. So thanks again, everybody, for joining us today. We will have our following webinar on December the 5th with Dr. Uher's lab, and we look forward to having you. So thanks again, everybody, and have a great day.